Hello, welcome back to Math with Patrick. Today is February 1st, and we're solving the 32nd problem from this Daily Epsilon calendar. Now that it's February, keeping track of what number problem we're on is going to be a little bit trickier. All right, let's find the area of the two regions bounded by these equations. All right, I'm already feeling like this is going to be a calculus-y problem because I'm finding the area of some regions. I could potentially solve this with geometry, but since I have this x squared, that's not going to be a straight line, and it's going to be pretty hard, maybe even like impossible, to find the area of something that looks like this shape, unless I have calculus under my belt as a tool. So let's just see what it looks like. I'll draw a little sketch. So here are my x and y axes, and then apparently I'm gonna get two regions from this, so we'll just see what happens. Y equals x squared is like your classic parabola. That one's gonna have a vertex at the origin, so like right here at the center. And it's gonna have that pretty standard U shape that you could expect out of a parabola. Ooh, and I just realized I might actually need to zoom in my detail because this y equals x line, that is going to be a perfect 45-degree angle going up like this. And maybe you could tell there was a little bit of overlap here where the y equals x line was a little bit higher up than the x squared curve, but it's really hard to see, so I might need to change my sketch. Finally, x equals 2. Well, I know that these two intersect at 1, 1, and so x equals 2 is going to be a vertical line right here. So I should probably change my sketch and actually zoom in a little bit. Looks like I really only care about the first quadrant, and I really only care about when x is between 0 and 2. Here is that line y equals x, and then the parabola dips below that straight line, crosses right here, and then it'll be above it forevermore. And okay, my second sketch is a little bit inaccurate too, because I wanted to be able to fit the whole picture on the page, but I ran out of room. So let me make a better sketch. All right, so here's my better sketch. This way I can actually fit all three things on my picture. I have that parabola in red, I have that line y equals x in green, and then I have my vertical line x equals 2 in blue. I'm trying to find the area of the two regions bounded by these three different equations. And so I'm going to be looking at this part right here and this part right here. And kind of like I predicted at the beginning, since I do have this curved border, really the only way that I know how to find the area of this is with an integral. It does take calculus. Fortunately, it's not too hard of an integral. I'm basically just going to be using the power rule on these things. So here, let me first set up my integrals. To find the area of this first part, I need to integrate from 0 to 1. And that's these values right here. I'm looking like left to right. Where is my shape that I'm finding the area of? And then to find the area of the shape, I want to do the top curve minus the bottom curve. And essentially what I'm doing is I'm adding up a whole bunch of, you could think of it as adding up a whole bunch of rectangles along the way between 0 and 1. And I'm just calculating the heights of all of these rectangles along the way. This is the basis of where an integral comes from. It's called a Riemann sum. And it's just the idea of adding up a whole bunch of tiny little rectangles, super, super thin, paper thin rectangles to get the area of a weird, curvy, bordered shape. So the top function here is going to be this y equals x. So I want to choose, well, I would really like to just be able to say the top y value subtracted by the bottom y value. This gets me that vertical distance that I wanted. But since I'm looking left to right, I'm looking in that x direction, I would actually like both of these to have x as their variable instead of y. So the top function, it just tells me that y is equal to x. That's easy, so I could just put an x here. And then it tells me that the bottom function is x squared, so I could replace that one with an x squared. Cool. So this is an integral expression that calculates the area of that first shape. and I should add it to the next integral that calculates the area of the next shape. That'll be from 1 to 2, because again, I'm looking left to right, trying to figure out where is that shape that I'm worried about. And here it looks like my top and bottom functions are flopped. So my top function is the x squared, my bottom is just the x, and then I still have this dx at the end of my integral, and this just reminds me that I'm checking the area or integrating from left to right. You could totally integrate from like bottom to top with a dy direction, but maybe that's for another video. So if I am able to evaluate these integrals and figure out their areas, then I will have solved the problem. So right here essentially should be just the number 1, but I kind of have to set out and prove that it's actually the number 1. I'm going to use something called the power rule that helps me integrate. For now, if you aren't sure what it is, you could think of it as a formula, but there are ways to prove why this works. Essentially, if you integrate some x to the power of, I don't know, let's just call it p, you could raise the power by 1, so it'll be to the power of p plus 1, and to kind of compensate for that, you have to multiply it by 1 over p plus 1, or in other words, you're dividing it by p plus 1. And so this is what I'm going to do for basically all 4 of these x's here. And so I'll take the antiderivative or integral of x that raises the power by 1, and I need to divide by that power. And then this part, the power will go up by 1, and I need to divide by that power. And then the notation changes a little bit. This part just tells me to evaluate it at 1 and 0, and we'll deal with that in a sec. I just wanted to finish my integration step. Using the same power rule, I get x cubed divided by 3, and then minus x squared divided by 2. And again, I need to evaluate it at those bounds from 1 to 2. And the idea here, this is actually coming from that fundamental theorem of calculus, kind of the basis of just learning calculus in general, especially the integral part of it, is now that I've found these antiderivatives, I'm allowed to plug in the top number and subtract the value that I get from plugging in the bottom number. And this is the same as these areas on the graph. So I'll plug in the top number 1, and I just get, I get 1/2 times 1 squared minus 1/3 times 1 squared. So this 1 cubed. But the 1 squared and the 1 cubed don't do much. So I'll just say 1/2 minus 1/3. And I need to subtract what happens when I plug in my lower bound. But my lower bound is just 0. So 0 minus 0 is going to get me a 0. So this is my evaluation for that area on the left side of my graph. That's the little sliver right here. And I'll add on evaluating this part. I'll plug in that top bound, that 2, and this time it actually does matter when I cube it. So I'll have 1/3 times 8 minus 1/2 times 4. And then I'll subtract what I get after I plug in the 1, which will just be another one of those 1/3 minus 1/2. Okay, so this apparently is just the number 1. Now I got to prove that too. So 1/2 minus 1/3 gives me 1/6. And so actually over here, 1/3 minus 1/2 gives me negative 1/6. But I'm subtracting the negative 1/6, so that's a plus 1/6 there. 1/2 times a 4 is a 2. This 0 does nothing. And then right here, I still have a fraction, 8/3. Though the 1/6 and this 1/6 can combine into a 1/3. And then when I do 1/3 plus 8/3, I get 9/3, which is the same as 3. So then I take my 3, subtract it by 2, and I just get the number 1, which is today's date. That means I've solved this problem. Got it. So these two areas together combined give me the number 1. Well, that's it for today. Thanks for coming along and solving this integral problem with me, finding some areas on the graph, and I'll see you in the next video. Bye.